When most people start in the electric trade, insulation seems simple. So you hear that porcelain is an insulator, XLPE is an insulator, oil is an insulator. But in real equipment, transformers, lines, bushings, cables, insulation is not just a material. So it's a system designed to control those electric fields. So that's the key idea for this entire series. If you understand what the electric field is doing, insulation stops being mysterious. So you can look at equipment and predict where stress will build and where is most likely. So let's start with something basic. So when a conductor is energized, the voltage creates an electric field that fills the space around it. The shape of the field depends entirely on geometry. A smooth round surface spreads the field evenly, where a sharp point will squeeze the field into a tiny region. Now, this matters because insulation doesn't fail from voltage alone. It fails when the electric field becomes strong enough to break down the material around it. So let's take air, for example. At a low field strength, nothing happens. The air molecules stay neutral and stable. But once the field gets high enough, electrons accelerate. They hit other molecules and they knock loose more electrons. So this chain reaction is what we call an avalanche. Avalanches link into streamers. And when a streamer spans the entire gap, that's a breakdown. So that's the simplest kind of insulation failure, air breakdown. And it starts with the electric field becoming concentrated enough to trigger those avalanches. But in a real power equipment, we rarely rely on air. We rely on solid and liquid dielectrics, epoxy, ceramics, XLPE, transformer oil, paper. So these materials work by polarizing. Their molecules shift slightly under the electric field, resisting conduction. As long as the field stays within limits, the material handles this just fine. But any defect changes the picture. So a tiny air void inside XLPE, a bubble in oil-impregnated paper, a bit of moisture trapped inside epoxy. So these imperfections distort the field and concentrate stress in small regions. Inside a void, a breakdown strength is much lower than the surrounding solid. So instead of the entire insulation failing at once, only the void breaks down. That tiny local breakdown is called partial discharge, or PD, and it's one of the most important concepts in insulation. So PD doesn't destroy equipment instantly. It eats away at the insulation a little at a time. Chemical byproducts form, carbon tracks develop, and microscopic trees grow through the material. Now, over months or years, a local defect will become a full breakdown path. And that's why cable failures often appear sudden, even though the damage was building slowly. Now let's move to something technicians see every day, outdoor insulators. So whether they're porcelain or polymer, their job isn't just to block the voltage. It is to control the electric field along the surface. And the surfaces are exposed to the real environment. Humidity, dust, salt, fog, pollution, ice. A clean insulator has predictable behavior. The field follows the sheds and the creepage distance. But contamination changes everything. So when moisture dissolves those salts or industrial residue, the surface becomes conductive. Current begins to flow across the surface. As current heats the moisture, parts of the insulator dry out. And these are dry bands. So the dry bands interrupts the current path and the electric field spike at the band edges. Arcs can jump across them, and then under the right conditions, these arcs grow into a full flashover. Now, polymer insulators add another layer, so hydrophobicity. So they're designed to repel water so the surface doesn't form a continuous film. But heavy pollution or aging can reduce hydrophobicity temporarily. Now, when that happens, the field shifts again, and leakage increases until the surface recovers. Now, all of these examples, voids, moisture, pollution, electrode, shape, demonstrate one point. Insulation failure comes from changes in the electric field, not just the applied voltage. So the field distribution is what determines whether insulation stays stable or begins to degrade. And this brings us to the insulation ratings. So the BIL, or the basic impulse level, is not just a number. It's chosen so that the insulation strength is higher than the worst case electrical stress the equipment will ever see. So lightning surges, switching surges, temporary overvoltages, so these define the stress curve. Material behavior and geometry define the strength curve. Now, insulation coordination is the engineering process of matching these two curves. You don't overbuild, you don't underbuild. You select the insulation strength that provides acceptable reliability at an acceptable cost. So insulation works by controlling electric fields. Breakdown happens when the field becomes intense or uneven. Partial discharge starts when tiny defects turn into concentrated field regions. Surface contamination changes how the field flows along the insulator. And insulation coordination ensures the system strength always stays ahead of the system stress.